let's get started and go download the required software we need. The first thing we're going to do is go to msdn.com and we're going to go download the Visual Basic Express, which is going to work as our development environment. So once you go to MSDN, let's go to Visual Studio Express, and we'll get to the Express page, and what we are going to do is go to the download. I'm clicking download now. And when our next page comes up, we're going to scroll down a little bit and find Visual Basic 2008 and download that. And once it's all downloaded, then you go ahead and run the application and do the installation. Okay, so now it's time to download the Advanced HMI development package. That is hosted on sourceforge.net. So let's go to www.sourceforge.net. And once that page comes up, the quickest way to find the software is to do a search on Advanced HMI, all is one word. Now after you perform that search, it will be the very top item in the list. And just follow the download links and download that software. And after you get everything downloaded, then you want to unzip it so you will have your files open and ready to use in the next step. So very quickly, I just wanted to show the hardware I'm using for this demonstration. I have my PC hooked up to a SLIC 504 with a null modem cable, and that is all I'm using for this demonstration. You see there is a one-rung ladder program with a timer and a B30 to reset the timer. So now let's go on to the next step. Okay, let's get started building the HMI. Browse to the files that you downloaded and unzipped from sourceforge.net and double click the solution files, the .sln. Once you do, you'll get a little warning just because you downloaded the file. Say OK to that warning. So our first step is to go up to the build menu and let's build it. We have to do this because it is a source code project. We have to build the source code. So now go over to Solution Explorer, double click main form to open our form. Now let's go over to the toolbox and scroll all the way to the top, and you will see here's all of our components. Grab a digital panel meter and drag and drop that to the form. Once you do that, go down to the properties window and find the PLC address. Now let's change that from N7:0 to T4:0.acc so that we can monitor the accumulation value of our timer. Now I'm also going to change the gauge text to T4:0 running, just so the meter will show us exactly what's being displayed by the meter. Now if you notice, there was a component automatically added called DF1COM1. That's actually the driver, and if you look at the properties, this is where you can change the COM port if you're using other than COM1. Okay, so let's go back to the toolbox and grab a momentary push button and drag and drop one of those to the form, and go over to the properties window, and the PLC address will automatically be B3:0, which is fine. We're going to use that. Now I'm going to change the legend text and make it say reset, since it does in effect reset our timer. So once that's done, let's go up to the top to our VCR play button and actually run the application. Now once the application is started up and running, if you are connected to the PLC and have power, it will search for and find the baud rate settings and then begin reading the values out of the PLC, and you'll be able to see your accumulation value of your timer, and when you hit the reset button it will reset, and there we have it. We've built our HMI.
Electric. In this presentation, we're going to demonstrate the automated HMI example that's installed with the OPCsystems.net product. Under the program group OPCsystems.net, you'll find the automated HMI application. This application is designed to automatically set up data source configurations, data logging, trending, alarm limits, and then the HMI clients will automatically adapt themselves based upon what data source is defined. So with one click of the mouse, we'll be able to automatically add a filter bed to the application. If we select Edit, Filters, and then Add Filter, we see that a new filter bed is added to the tag configuration. It is set up for alarm limits, it is set up for trending, and we see the result of the HMI now being updated here. If we launch a second example of the automated HMI application, we see that it reads the tag configuration from the data source and automatically displays the one filter that has been added. Now if we come back and add another filter from either of the applications, we see that both applications update themselves automatically. So you can see that applications could be running locally or remote and be automatically kept up to date with the very latest data source configuration and operator interface information that is set up in the data source. I'll add a few more filters here. We see that we're getting some alarm indications on the operator interface. We can open or close any of the fill or drain valves of any of the filters, and we'll see those as you click on those. You'll see the update in both applications. If you select the Trend tab, you'll see that there's real-time trending for each of the filters, both for the turbidity and the flow rate of each of the filters. And under the Alarm tab, you'll see real-time alarms for each of the filters for both flow rate and turbidity. Under the Setup tab, you can enable data logging, and that will automatically add data logging groups and the tags for each of the filters to be logged, and it will log it to the SQL Server engine that you specify here in the SQL Server name. You can also do remote connections to remote network nodes. To review the automated HMI example code, visit the website automatedhmi.com. There you'll see an example source code download section with a download button, and that's where you can download the Visual Studio 2010 code. Let's take a look at that code. So we have the Add Filter button, and when a user clicks on that, we're going to call the method Configure OPC Systems, and this is a routine that has been set up to automatically configure the tags. So here in the routine Configure OPC Systems, we see that we're creating tags programmatically just by assigning the tag CSV import method, and that's through the OPC Systems component. The OPC Systems component is free to use, and it's also well demonstrated in the WinForm example code. If we take a look in the program group OPCsystems.net, we see the WinForm example code right here. And there you'll see other examples like configuring recipes, reports, data logging, alarms, security. Every single configuration attribute of the OPC Systems component can be modified through the OPC Systems component. And once we've added the tags and defined the alarm limits, the next thing is it would automatically add the form for the filter bed, one for each filter. Here we see the method Add Device, where it's adding a filter to the main window. And if we look at the code for the filter bed, there you see the HMI controls are set to the tag names based upon which filter it is that we're adding. So the device number ranges from 1 to 25, depending upon how many filters you've added, and so the code for each of the filters is the same. It's just this variable called device number, which represents the filter number that is being added to the HMI application. We also see a routine called Update Pens, that's a method, in the main window code, where it's updating the trend window for each of the filters for both the flow rate and the turbidity. So here it's setting various pen attributes based upon color, description, engineering units, and its originating source. And then it's setting the pens property based upon the pens array that we have defined. The pens property is in the OPC trend control. If you have more questions about the automated HMI example, visit the website opcsystems.com. Under the Contact Us page, there you'll find our contact information along with a link to request a free product demonstration.
In this video, we'll take a look at some good practices for accessing PLC data from an HMI. Often we're met with a choice of whether to hack something together that'll work for now, or to engineer a well-defined solution with traits like good performance, reliability, maintainability, and portability. The basic practice we'll be discussing is setting aside a block of standard memory in the PLC to serve as an interface between the PLC and the HMI. For reference in this video, we'll call it an interface table. This is in contrast to a more ad hoc approach of just pointing the HMI objects directly at whatever data and I/O in the PLC we're interested in, some memory here, some control registers there, some inputs, some outputs, and so forth. The interface table is an alternate approach where the HMI reads from and writes to a well-defined area of PLC memory. The PLC program in turn services the interface table by mapping that table data to the appropriate areas. Importantly, this allows the PLC program to maintain control over the HMI's access. Why might it be worthwhile to do this? One reason is performance, particularly as related to the efficiency of communication between the HMI and PLC. Simply put, data that is less scattered leads to fewer data packets clogging your bus or your network, and therefore potentially better system responsiveness. Data packets or message frames carry a lot of overhead unrelated to your data. Concentrating HMI data into an interface table results in more data per packet, and hence fewer packets and less overhead. Next up is reliability. The main point here involves keeping the PLC, which is engineered to be extremely reliable, in control wherever possible. You may be able to directly control a PLC's outputs with an HMI, but having the HMI instead write to the interface table allows the PLC program to maintain a degree of control. The PLC program can, for example, implement an HMI enable bit whose value could depend on things like completing a startup sequence, the current COM status, or various safety checks. By the same method, the PLC program can referee the HMI's reading of data, particularly I/O, ensuring its validity prior to enabling HMI access. Let's take a closer look at this simple implementation of an interface table in an RSLogix 500 application. I've got a table of bits here which serves as my HMI interface table in this toy program. For example, the HMI can write to these bits to control PLC outputs. If the running PLC program has enabled HMI control, then a simple subroutine copies the bits from the HMI interface table to the outputs every scan. In this case, we've copied bit by bit because we like to be very explicit when allowing HMI control of outputs. In servicing the HMI reads of I/O, we just move or copy entire words of input and output bits to the interface table for HMI access. The development and maintenance of a system is determined in large part by its design and its documentation. If we take kind of a haphazard approach to how we interface the HMI to the PLC, we may end up making more work for ourselves or others down the line. If we want to make even minor changes to the PLC program, which happen to affect the areas accessed by the HMI, then the HMI or HMIs will have to be reprogrammed as well. And hopefully the person changing the PLC program will be aware of the affected HMIs, both local and remote. However, if we've implemented an HMI interface table in the PLC, there may need to be no change to the HMIs, only a remapping of the interface table in the PLC to the various PLC data areas affected. The presence of the interface table in the PLC code or configuration is itself a kind of documentation, if you will, making it clear to those modifying the PLC program that there are HMI requirements to be considered. But ideally, the interface table is described in a document that is kept up to date as changes are made to the system design, HMI functionality, and the PLC implementation. This is particularly useful when the development or maintenance of the system entails more than one person working on it. The interface table is a clear method of communication between those working on the PLC program and those programming the HMIs. With a well-documented interface table, those working on HMI code don't need to know about every little change being made to the PLC program and don't have to be concerned about exactly how, for example, the I/O is implemented, be it embedded, expansion, or remote I/O, etc. And even if you are the only one programming the system and somehow are the only one who ever has to maintain it, you'll appreciate not having to relearn the intricacies of the PLC program and I/O structure just to make a small change to the HMI program. Finally, the approach we're advocating here will make your designs more portable, which is to say reusable. This comes into play if you want to reuse your code with new hardware. Using a well-designed interface between the HMI and PLC, as we've been discussing, decouples to some degree the PLC and HMI configurations, allowing a more standardized approach that is less dependent on the peculiarities of the particular hardware, making it easier to upgrade to new models or brands, as is often required by cost, changing company policies, or obsolescence. Okay, to recap, we've been talking about using a well-defined and documented data table, or tables as the case may be, as an interface between the PLC and HMI. Now, this approach is not novel. In a generalized sense, it's used in many areas of engineering to improve technical solutions. In software engineering, it's called encapsulation and is used for the same reasons we've been discussing here: performance, reliability, maintainability, and portability. That's all for now. Please visit us at rotecautomation.com.
The ability to be able to easily add an Aussie network to your current machine design can be a huge benefit to any machine builder. Let me show you how easy it can be. As you can see, here's my current controller and HMI panel. This is what we want to add, this Aussie network to. So here's the master, an I/O block, a start-stop station, as well as a signal column. So that's the task. The first step is we come over to the actual hardware configuration. Here's the actual controller itself. I have a little filter box checked in the hardware catalog, so that means only the available parts that go in that rack are available to us. I can easily find it. It's the Aussie master. Here it is. Give focus to it. Drag and drop it into the project. Now that's done. Let me go to the network view, and as you can see, I do have my current HMI and controller on Profinet, and I also have the Aussie master. How about the field devices for the Aussie network? Well, from a global library perspective, I have the ability to build up my entire network of all my field devices, including attributes. I can actually go back and save that to the global library, and every single time I have a new project with that exact same type of field device, I pull in the project and you're done. So let's go to the global libraries. Let's go grab the first I/O block, drag and drop it in. If I want to change an attribute, just give focus to it, right click and go to properties. I want to change his address to 19A here. That makes sense, right? So let's go down and find the 19A address. Perfect. Attributes changed. Okay. How about the signal columns? Drag and drop him in. And then last but not least, start stop station. Okay, so how about networking? Well, all I got to do is mouse over any one of these interfaces, drag it up to the master and let go. And let me go grab the next one, and as you can see, just like Profibus and Profinet, networking can be that easy. So now I've got my hardware done and my networks. How about code? Well, the first thing I'd like to do is go to the master, the actual controller itself, go down to properties. Let me go down to the system clock memory bits, and what I want to do is I want to enable the clock memory bits because I want to use this later so I can actually pulse something. Enable it, and let me actually choose a byte here of 649. And as you can see, I have my clock underscore and whatever hertz I want to use for my pulses. I just need to remember that for later for my tags. Well, let's go back to the program blocks. Let's go add new block, organizational block, that's correct. Click OK. Accept the default name, that's no problem. Now I want to do a fill-in circuit here. Let's go grab a normally open contact, normally closed, as well as a coil. And let me go complete the fill-in circuit with another normally open and tie it in. So now my code is done. So just like the hardware configuration I had for my field devices in the global library, I can do the exact same thing for a tag database. I can create it once with the exact data structure I want to use, save that global library, and reuse that, creating engineering efficiencies in your daily work. Well, let's go to libraries. Go to simple Aussie tags. Let's drag and drop it over to PLC tags. Here they are down here in the details view, so now I can start programming. Go drag and drop stop into the code, to the normally closed contact, start to the normally open, and go drag and drop motor 1 to the coil. Go click on control and drag it back over, and now I have a completed start stop fill-in circuit. How about actually doing some enunciation? Well, I want to do is create some new networks. Go grab a normally open contact as well as a coil. I want to go over here to network 2 and just copy and paste this in a couple of times. I'm going to create 3 networks. Now that I've done that, I'm going to go give focus to them, and I want to use the motor 1 coil as anything to use in our normal code to enunciate. If that coil is actually pulled in, that means we're going to enunciate something, start, stop, whatever. Well, all I got to do is go grab him, drag and drop him in, and I want to go grab start stop tag for this exact start stop station, because you see I have one actual LED, and if it's high you're going to see it turn on, if it's low it's going to be turned off. So let's go grab that tag for our start stop station. There it is. I can go back and grab the motor 1, click on control and drag it down. I can actually do that twice. So now I want to enunciate with our signal column. So let's go grab machine run, drag that over to our next coil, and then machine stop is our next one. However, I have to have the inverse state for our yellow LED, and what I need to go do is change that contact to a normally closed contact. Okay, so I've got all my code enunciation. How about faults and diagnostics? Well, I've got one more line here. What I want to do is go grab the fault LED here, and it just happens to be the red LED in this particular configuration. And I also want to actually be able to pulse this red LED so you can see anything from a machine faulting perspective. What I want to do is go over here and go back to that clock bit, double click, use smart type and just type C, and there's our clock bits. I want to use 1 Hz. That's exactly correct. However, I have to use some kind of diagnostic block in order to get this to function properly. If I go back to my instructions, let's go down to diagnostics, let's go grab the LED, drag it in front of our pulse. And what I want to use is the actual controller itself to actually generate this fault. So on the input side, just type in, with Smart Type, just type in S, there's the S7-1200, click Enter. And then the LED itself, I want to use the error LED. So let's use number 2. And the retained value is going to be error underscore CPU. And then I want to go back and define that tag. I want to make it an integer. Click Define. However, now I need to compare this against what's the normal and faulted state. So what I want to do is go over here and grab a compare. Drag that in front of this pulse. Grab this retained value, drag and drop it up. And last but not least, I need to figure out exactly what the states are of this LED. If I go down to LED block, just hover over it, go to Read Status, open up the Help menu. So the 1 equals permanent switched off. That's exactly what I was hoping it would be. Go give focus to it and copy that. Let's go back to our tags here. Double click on them. Go find the user constants. Name this exactly what we just had, so paste it in. 1 equals permanent switched off. Just move over. We want to use this as an integer. That's what it needs to be. To use Smart Type, just type I, click Enter, and 1 was the state. All I need to do now is actually split screen that and go find the compare value in our code. There it is. Give focus to this user constant, drag and drop it in. Now our code is complete. Just give focus to the main CPU and click the download arrow button. So now it's going to compile the fact that we have this new hardware configuration, including the Aussie network and all the field devices, as well as all the new code and the diagnostics that we just created for this particular system. The load button is now available for us to hit. Now it's going to load everything we just compiled and created for this Aussie network into the actual CPU itself. Once it's finished loading, we should see some green LEDs. I can click Finished. As you can see now, the entire system's up, fully functional. All I got to do now is go here and see I can hit the start-stop station. Everything runs the way it's supposed to. And in fact, I can go over and fault out the Aussie network. And this is the actual input for our start-stop station. It should fault. So the fault logic is working the way it should be. And the beautiful thing about this HMI is I went to service support and downloaded faceplates and function blocks for additional Aussie diagnostics. And this is completely free of charge. If I come over here to faceplate and hit Start Aussie Diagnostic, as you can see, I do have a fault on address 5. That is the start-stop station. And in fact, it's a hardware configuration error, so that means that the Aussie network is not plugged in. I was able to do this entire hardware configuration and all the programming in just a matter of minutes. Now that's engineering efficiency.
This UCSD TV program is a presentation of University of California Television for educational and non-commercial use only.
It's a world where computers read our thoughts and emotions. 3 teams of UC San Diego researchers are pioneering a new field called brain-computer interface.
Walk.
Bruce Kelly hopes the new research will help keep him mobile as Parkinson's disease progresses. The degenerative disorder can make Kelly's legs freeze up, especially in narrow spaces. These white columns in the motion capture lab at the Supercomputer Center simulate an elevator.
Freezing episode during the turn.
UC San Diego cognitive scientists Virginia Dessaw and Howard Poisner are using an EEG cap to monitor Kelly's brain. The 64 sensors on his scalp read electrical signals.
The idea with the Parkinson's patients is to try to detect from the EEG signal, so from the voltage measured at the scalp, whether they're about to have a freezing episode, so whether they're about to have freezing of gait. The future application would be then, if we can detect that, we can present visual and or auditory cues that would help them overcome that freezing of gait.
Parkinson's patients are known to very heavily rely on external visual or auditory cues in order to guide their movement. So they may be unable to initiate a movement. You put chalk marks down on the floor, they can see where to place their feet, and then they can begin to move.
The research team is testing 10 people with Parkinson's. The ultimate goal is to develop a portable EEG device that could prevent their legs from freezing in the first place. Sensors could be embedded in a baseball cap or a headband. Virtual reality glasses would display visual images to guide the patient. Emerging technology could help retrain the brain and get people like Kelly out of a pinch.
Oh, you're doing good.
With brain-computer interface, or BCI, a computer not only reads brain activity, but sends signals to an external device, like a wheelchair or a robot, to execute an action.
Now, we're not reading people's thoughts as they're, thinking about Shakespeare's lines. That's a long way off. But reading their motor cortex thoughts about how they want to move in which directions and so forth, that's very doable.
Upstairs from Poisner's lab, Seping Zhang is developing ultra-portable BCI hardware, from headbands to helmets, at the Swartz Center for Computational Neuroscience.
So basically we put 16 sensors on the subject head. And as you can see, this setup takes about 1 minute.
No gel or wires are needed for this prototype. 16 spring-loaded electrodes read the user's brain waves and send those signals to a Bluetooth-enabled phone or tablet. Zhang says wireless headsets could help the general population with everyday activities like driving.
So if a device can detect and track the cognitive states, in this case, for instance, drowsiness of the drivers, and then decode the signals, trying to give the feedback or the warning signals to the subject when they fall into sleep on the wheel, and then we can save lives. So you as a subject, you need to look at numbers one at a time.
Zhang also helped develop a BCI application for people who can't physically dial the phone. A researcher demonstrates with a headband containing 4 electrodes. He can call a phone number simply by looking at numbers on the screen one at a time. His brain signals are then sent to the cell phone for an automatic dial. Tucked away in another corner of the Supercomputer Center, musicians show how brain-computer interface can read and express emotion. Scott McCaig is the composer and violinist. There's a cellist, a flutist, and a so-called brainist.
You're playing the brain.
That's Tim Mullen. The cognitive science graduate student focuses on one of 5 distinct emotional states, feeling it fully inside his body. As Mullen enters into the feeling of shyness, 64 sensors on his EEG cap send brain signals to the MobiLab control room. Software translates his mood into a bass tone, which comes through the loudspeakers.
This feeling is of one who is uncertain, quiet, shy, and sensitive.
The musicians then play the piece that corresponds with this ground tone.
The audience would know whether it worked by seeing whether the description that was given of that state, like shy and sensitive, matched the quality of the sound that came out.
In this rehearsal, it worked, proving that a computer can not only decode basic thoughts, but primal emotions. And the brainist could communicate his feelings through music without even lifting a hand.